Hello, welcome to week 5, and this week, as part of the HeadStarter Accelerator, we uh, implemented a code-based RAG. Now, quick overview as to what we'll be going over. If you're not familiar with RAG, then RAG stands for Retrieval Augmented Generation, and it solves a critical problem with traditional LLMs. It solves because training LLMs with new data is extremely expensive. Hundreds of millions of dollars estimated are needed to train LLMs, and retraining is required to update the model's knowledge. Models have fixed knowledge cutoffs. Um, so let me just summarize that for you. So, as you are somewhat familiar and or should have been aware of by now, creating and training an LLM isn't cheap. These large companies who put out LLMs on like an almost like regular basis spent billions and billions of dollars just um, on the resources alone to train their models. This should be able to train their models repeatedly by either ML engineers and or ML teams, usually in like these big data centers, um, and have like these huge AI centric units, which it is like fully optimized to train LLMs with like 40, 50 GPUs in this one like 5 foot in width like box. So it gets pretty expensive. So retraining is required to update the model's knowledge. So the knowledge of most LLMs are static. They're static because, as you may know, there's a bunch of information being released on a daily, on a day-to-day basis. And as I'm speaking right now, there's probably like about 6 papers being published, like or like 20 full-stack tutorials being published on YouTube that you could have been watching instead of me. But yeah, then the last part is models have fixed knowledge cutoffs. By that I mean, since you train the model on a fixed dataset and your dataset isn't dynamic, um, the date in which your dataset is derived from is the context in which the LLM is using. So, say you were to get data about women in the 1920s, 30s, then and use it today, your LLM would probably be canceled in a heartbeat. I assure you that, because data from back then wasn't isn't as reliable as it is today. Um, Most of the assumptions about women back then were made by predominantly male white like scientists, and with little to no knowledge about like the other sex and or whatever other gender there was at the time. They didn't feel like they needed to at that time until all these other problems came up and modern medicine kind of sped up within the last couple of decades. So if you were to use like data from that period of time, then as I said before, your LLM would probably be canceled and be worthless. Um, if you're not already aware, the GPT 3.5 model is trained on a 2020 dataset, which I was made heavily aware of, but I mean, 2020 um, feels like a point in time, a fixed point in time, in which it feels like a cutoff um, towards society's progression. Like I felt like we're going to go like pretty decent, then this um, disease spread like wildfire and fixed and like altered some paths evidently. Work from home, the introduction of work from home definitely impacted some businesses as well. and people became more and more accustomed to a hybrid and or fully virtual lifestyle. Thus, some companies fell in the water, and some companies soared through the skies during that period of time, and job trends as well. People were looking for more and more engineers to kind of like help them in these periods of in this period of time in which everything was practically remote, and the standards for engineers then weren't as the standards for engineers at that period of time was lower than the standards of engineers before them. Well, I'd say the standards for engineers as now and in the to mid early 20 early 2000s and mid 2010s were a lot higher than they were during that period of time, that's for sure. And now, that's for sure as well. So, moving on, RAG allows us to dynamically inject new knowledge into LLM responses, keep information up to date without retraining, provide relevant context for specific queries. How RAG works: embedding processes, vector search, LLM integration. So to start us off, embedding processes convert text into numerical vectors, embeddings. These vectors capture semantic meaning. Similar concepts have similar vector representations. For example, Obama and president will have similar embeddings. So if you derive, so it's deriving the context. Yeah, so it's deriving the embedding scores from the context. And say you have an article on U.S. presidents, then Obama being listed within that list would obviously raise the score of the vector embedding. So another example of a quick example of like vector embeddings. So you have almost infinitesimally infinite possibilities and outcomes. So are you have a base context. So I'm using this game as an example. It's called Little Alchemy. Base context of earth, fire, water. So from that, you create relations. You create relations. So between earth and fire, you got lava, earth, fire, earth, lava, earth. You get volcano, and then earth, water. You get mud, and earth and steam. You get geyser, and etc. etc. So it's essentially just creating relations to the embeddings, to the inputs. So vector search. Query is converted to embedding vector. Search for similar vectors in database. Uses cosine similarity to find closest matches. Returns most relevant document/context. So um, vector search has been kind of a rage within the community, but I believe vector search has been implemented for a while with tools like Algolia and whatever. Algolia is what you see in like these tech stack documentations. So these maintainers of the documentation would use Algolia for like quick and easy search, and you'd have like the ability to like get the context of the entire documentation, and based on your search, it'll return like the links to said documentation. Um, and as far as cosine similarity goes, so essentially what that is you have two input contexts, and you're going to derive the similarity between them. So if you have, say, hello world, let's just, um, yeah, say you have hello world, and here, oh, hello world here as one, and hello world again as the second input. So the similarity between them would be 1 to 1, or just 1. But if you change the punctuation a bit, then the similarity between them would be, um, hold on, maybe not that. Lower bound, lower bound, and yeah, the similarity between them would be less than 1. So, and as for vector databases go, I believe Chroma, MongoDB, and Supabase have vector search and or databases that you can try out. I personally like Subase's vector database as it amps up PostgreSQL as um, it is, and somewhat puts it somewhat on par with MySQL. Don't come for me. Don't come after my statement. But yeah, I said what I said. But yeah, it's mainly used for developing applications, but you can use it for these big search engines as well. Not necessarily search engines, but search implementations within like a large data set or input. But yeah, it returns the most relevant documents as context. So based on the query, it's going to match case um, the query to what's already within the database and or input. So it's similar to how Google's doing this. So type script and it's generating all these like links and titles as I type. It's like that. So LLM integration. Retrieve context is added to prompt. LLM uses both its training and the new context, generates more informed and up-to-date responses. So like I said before, um, say you have a bucket, and from that bucket, the AI is from that bucket you have the inputs, and the input is being fed into the AI like a I cannot find an analogy right now, but the input is being fed into the AI, and you can either use whichever mathematical representation of growth and or decay you want, but the um, input can either grow or decrease, and or self and or self sort or self like it can account for itself and its relevancy. So a proposed idea I had a few weeks ago was you have this data frame in which it gives you in which it is generated by a mathematical function in which it gives the relative context of an or score of x. So if x is lower than the minimum within the database in which I want to um, push that data with the x with the data frame in which it holds a value. So if it that data frame value from the input is lower then the lowest data frame value that's already within the database, then it's not going to be sent to the database. Um, but if it is greater and the AI and the function is more certain in its calculations, then uh, remove the smallest it would remove the smallest number, which is generated by the mathematical function. So, and coerce and in parallel, it would retrieve the information from the database and update it as needed. So it would retrieve the information from the database, update the contents and context, specifically the data frame in which the mathematical function is used, and and reevaluate itself upon new inputs. And and it would be more like tuned to the person's needs. For the example I'm giving, it was a hackathon idea that I came up with, but we didn't have time and we pivoted. But yeah, moving on to the code example. So we are going to go over this part, this diagram right here. So we have the user query, how is JavaScript parser used within the context GitHub repository. Then we generate the query embedding, send out to the Penscone vector store, which is on the right. Um, then we get the relevant pieces of code. Then we feed it into the prompt, and the prompt slash LLM. We're using Llama 3.1 via the Grok API, and it gives you the answer. The LLM spits out the answer with the derived context, which was meticulously picked based on its vector embedding score in similarity to the query. So we are installing these libraries: Pi, GitHub, LangChain, Challenge Community, OpenAI, Tick Token, Pinecone Client, LangChain, Pinecone, Sentence Transformers. Moving down, we have the imports, clone the repository. We have supported extensions and ignore directories. So you don't. These directories are pretty well known to have a lot of files on build time and or compilation and or generated via installations as package slash library installations. So we're gonna ignore these as it is too much context to derive from, and it would just hurt the LLM as a whole, hurt us and our profits as a whole. We have a function get file content. We have a file read, uh, file read pattern. So file path, read permission, and encoding ETF. This is important because with encoding ETF, it accounts for the spaces and or special characters within within the file input, which is really important context for the LLM. And then we have another function, get main files content, file content. Then, like I said before, we are ignoring the ignored directories on directory checked, and for files, we are only looking for files with the suggested file extensions. Then we print the file content, etc., etc. Then we generate the embeddings with Hugging Face. So this function, you have text model name, which is the Hugging Face model name, sentence transformers, all MPNet base v2. Model equals sentence transformers, model name, then return model encode text. Text is I am a programmer and the embedding will generate as such. We get the embeddings. Then we set a pinecone. We're using 768 dimensions, but you can use however dimensions you want and which fits your needs. Then the metric is cosine, which enables vector search. Oh, well, somewhat. But we initialize pinecone with the index we created. Then profile content page document. Okay, so we input the embeddings into the Python vector store client slash constructor. Then from that we loop through the file content in which we extracted from the GitHub repository. We initialize document and page content is going to be file at the name property and new line file at the context property. Then the metadata is going to be source file name. Then documents at append doc. Then we're going to initialize the vector store with the Python vector store method from documents, and documents is going to be equal to the list of documents, and the embeddings are going to be the Hugging Face embeddings, and the input index name is going to be whatever we initialized and or created the Python index as, and the namespace is going to be the GitHub repository. We're initializing the LLM, so we're initializing the Grok API with the API version and the API model and version and the Grok API key. Our query is going to be how our Python file is parsed. Then raw query embedding, get Activate embeddings, query raw embeddings. So these are the contexts. Oh, these are the returned embeddings from the query. Again, okay, so moving on. Top matches Python index query vector is raw query embedding to list top k include metadata true namespace, and this is the top matches for the query Python parser. Moving on, we are initializing context with items object with the property of text, and from top matches property. Then we are returning the file title. Nope, the file contents. From the top matches, which match the query regarding the Python query. Then we are initializing an augmented query and or binding an augmented query in which we are using XML like syntax to give the LLM more legroom and or context about what we want. Then system prompts, a bit of prompt engineering. Then we put it all together to create this function perform RAG. Then we get a response, how JavaScript parser used, and put the response. Now the only downside and or bottleneck you may face when utilizing a codebase RAG is when you are dealing with large files which have a lot of context and derived context. So say you have like something like a Java file and you're writing like HTML within said Java file or JavaScript file, and you're writing HTML within said JavaScript file, and .html is going to be rendered on a DOM. You have it in a string literal. You have it in a string literal, and at some point you create the built-in. You initialize the built-in py element, which allows you to execute Python functions within the HTML DOM. Those are cases in which the context may throw off the LLM and or vector database. So yeah, I forgot for cosine similarity. Um, this is the Python code. It's typically written at, written with these written with NumPy. So you're initializing a NumPy array, then you're getting the dot product of A and B, then you're dividing that dot product by the um, product of norm A and B. This is the equation. So where A and B are vectors, A, B is dot product of A and B. It is computed as sum of element Y's product of A and B. A is L2 norm of A. It is computed as square root of the sum of squares of elements of the vector A. So thank you for watching, and hopefully this time my recording won't corrupt.